Intelligence, the final frontier. These are the field reports from Project Gepetto, a continuing mission to explore what emerges between human intuition and machine reasoning, and to boldly build what no single intelligence could create alone. Log entry 4. Mission status. Foundation. Data is not understanding, and benchmarks are not knowledge. The system was running and the models were responding, but I couldn't explain my own decisions. Many of them were correct, but the liabilities grew beyond my tolerance. So I had to harden my understanding.
A lot has happened since the last mission. The project moved in several directions at once. I went back to fundamentals and built the local intelligence field manual, starting with the conceptual primitives and the hardware constraints that shape everything on the Spark. The hardware stack itself had to change, and what was planned and what actually survived were two different stories. On the softer side, Gepetto evolved from a controlled chatbot to an agentic system. Local models with direct file access, a new HTTP layer, and a governance structure rebuilt from scratch. The model landscape shifted, runtimes were updated, and the entire system had to become portable. This mission covers the first part, the fundamentals. I had to learn and what happened when theory met my hardware. Let's take it from the beginning. The Gepetto library is where I publish my research. Freely accessible, see link in the description. One of its core documents is this: the Local Intelligence Field Manual, a living technical document focused on local LLM deployment, benchmarking and infrastructure design, written for and tested on the NVIDIA DGX Spark. Cognitive framework, methodological reference, public research log and strategic instrument, all in one structure. It's not a finished book. It evolves with the project. And it starts with the basics. There are over 2 million models on Hugging Face. The text generation category alone is already in the hundreds of thousands. LLMs you can download and run locally, and the pace is still accelerating. NVIDIA's playbook narrowed it down to what's officially supported on the Spark. But even within that list, every family was built differently. When I first started, I watched the same videos everyone watches. Run this massive model locally. The new whatever LLM is the best. I believed it, until I started building a system around it. The hard part was never running a model. The hard part is knowing which one to run for which role in which runtime and why. Pick the wrong model for the wrong task, configure it the wrong way, and the hardware doesn't matter. You get mediocre results from a machine that could do much better. A large language model predicts the next token in a sequence. That's the entire foundation. Every capability you observe, code generation, reasoning, conversation, emerges from that single training objective. Given everything that came before, predict what comes next. It doesn't produce a single answer. It produces a probability distribution, a ranked list of how likely each token is to follow. The actual token is then sampled from that distribution. That's why the same prompt can produce different outputs. The model didn't change. The sampling rolled differently. And how that sampling is controlled, temperature, top P, top K, directly shapes output quality. Almost every LLM you encounter today is built on the transformer architecture. Every token depends on every token before it. Generation is fundamentally sequential, and its speed limit, it's not compute. It's how fast data moves through memory. On the Spark, that's 273 gigabytes per second. On the RTX 4090 moves data 4 times faster. An RTX 5090 6 times. In raw generation speed, the Spark is not even close. But the 4090 has 24 gigabytes of VRAM, and the Spark has 128. With Blackwell and NVFP4, it can run models that don't even load on a consumer GPU. That's the trade-off. You can run large models slowly, or you run smaller models and use the remaining memory for longer context and larger KV cache. Either way, bandwidth decides the speed. Memory decides the options. The model is a static file of weights. It doesn't run on its own. The inference engine is the software that loads it, manages memory and serves requests. Ollama, VLLM, TensorRT, and many more. When something is slow or crashes, the cause can be in the model, the engine, or the interaction between them. In the first 2 episodes, we ran the same model on 3 engines and got 3 completely different outcomes. If you don't separate these layers, you start fixing the wrong problem. The large in large language models is relative. On modern local hardware, the meaningful question is no longer just size, it's whether the model is actually usable on your platform. Every LLM falls into one of 2 architectural families, and this is the first fork in every model selection decision. Dense models activate every parameter for every token. Predictable and stable, but compute scales with the full model size. Mixture of experts models contain more total parameters, but activate only a fraction per token. A router selects which specialized subnetworks handle each token, delivering the speed of a much smaller model at the quality of a larger one. Or almost. Before we move on, 3 traps that catch almost everyone. Parameters equal intelligence. They don't. A well-trained 8 billion parameter model from 2025 can outperform a poorly trained 70 billion model from 2023. Training quality matters as much as size. Trap 2. MOE means free quality. It doesn't. You save compute per token, not memory. If the model doesn't fit in your VRAM at your chosen precision, the active parameter count is irrelevant. And trap 3. Transformers are the only option. For local deployment today, practically yes. But hybrid architectures combining transformers with state space models are deployed and available. They are not mainstream, but they are real products. We know what the machine does. Now, what's actually inside the file you download? A model file is a collection of numbers, billions of them. That's what 70B means. 70 billion numerical values, each one shaped during training. How much space they take depends on precision. The same 70 billion parameters at 16-bit need 140 gigabytes. At 4-bit, only 35. But the file size is the floor, not the ceiling. At runtime, the KV cache grows with every turn of conversation. That's why a model can load fine and still crash 10 turns later. The weights didn't grow, the context did. Every LLM you run locally is built on the same architecture, the transformer. A stack of identical blocks, each one doing 2 things. First, attention. Every token looks at every other token and asks, what matters right now? That's what makes these models powerful. It also what makes them expensive. Double the context, quadruple the cost. Second, the feed-forward network. It holds the majority of the model parameters, roughly 60%. Attention decides what to look at. The FFN decides what it means. And here's the part that bites you in practice. Every token's attention data has to be stored for reuse. That's the KV cache. It grows with every turn at every layer. That's your why did it crash at turn 15 answer. The context consumed the remaining memory. Models don't process text, they process tokens. Subword fragments that the tokenizer cuts your input into. Hello is 1 token. A German compound word might be 5. A line of code somewhere in between. This matters because the context window is measured in tokens, not words. And different content burns through that budget at very different rates. English prose is efficient. Most tokenizers were trained on English heavy data. Code, German, Chinese, they all consume more tokens for the same meaning. So a 120K context window is not a fixed amount of content, it's a budget. And the exchange rate depends on what you feed it. Every model goes through a multi-stage training pipeline, and each stage leaves a behavioral signature. Pre-training gives it language. Fine-tuning teaches it to follow instructions and locks in the prompt template. Alignment shapes what it prefers to say. In RLVR, the newest stage, rewards verifiable outcomes. Does the code compile? Does the proof hold? That's what made 5.4 work as our thinker in episode 2. 14 billion parameters but trained to reason. When a model behaves unexpectedly, refuses harmless requests, stops generating early, ignores your format, The course almost always traces back to one of these stages. One more distinction. Knowledge cutoff is when training data ends. Permanent. Context window is what the model sees right now. You can feed it new information, but the model has no pre-existing knowledge beyond its cutoff. When I started building around these models, one thing became obvious. They don't behave the way you expect them to. The same model running on a different runtime can give you a completely different result. And without orchestration and memory, even a powerful model just sits there waiting and starts to break down after a few prompts. It gets worse when you let them interact with your files. To build around that, I had to understand what these models actually are. Not on the surface level, but deep enough to build on. There are off-the-shelf solutions that hide all of this from you. They work until they don't. And when they break, you have no idea why. That's why the Local Intelligence Field Manual for the DGX Spark exists. That's why this section had to come first. But this is where I stop for now. These primitives are the foundation, not the full picture. And yes, if you worked with LLMs before, most of this probably felt familiar. I thought the same, until I tried to explain why my system was actually behaving the way it did, and couldn't. And honestly, the best way to learn this is not by reading, it's by running a model, breaking something, and then understanding why it broke. That's how most of this landed for me.